Okay, so today we're going to talk about prefix sums. And so why should you use prefix sums and what do they do? If you think about summing values across a range, and let's say you want to do this query. So you want to sum values between the interval from start to end. And this is the half open interval. It doesn't matter too much right now, but let's say from index to up to index 5, but not including index 5. So you want 2, 3, and 4. So you'd have to add up 2, index 3, and index 4. And this is worst case order of n per query. So let's say you need to check 0 to 5, like the entire array, and you need to do that a lot of times. Then it'll take order of n per query. So you have to sum up all the values in the array. If you need to sum up ranges multiple times, then it might be more efficient to do some pre-calculation. So using an auxiliary array, this is also called like a prefix array, prefix sum or something. You can use this auxiliary array to speed up queries. And so you can have a prefix array of size n plus 1. So if n is the number of elements, then n plus 1. And then you add for every index of the prefix, it's the previous one, previous prefix plus the previous array number, or you can do it in a forward way, like int I equals 0 to n, the prefix I plus 1 is equal to prefix I plus array of I. That works as well. Or you can do -1, maybe 0 to n, and then plus 1 here is a little bit better, but it's the same. And you end up with this. So 4 plus 3, 4 plus 0 is 4, plus 3 is 7, plus 2 is 9, 4 plus 9 is 13. So you're adding up the two previous values to the next part in the thing, and then you end up with nothing in this original array, right? You have 6 elements in the array, n is 6, and at that array, you get the sum of everything. And so you can find the sums of a bunch of values really quickly. And so you might, yeah. And you can also do, this started with 0, but you can also do something where you just add it to the, like this, and you don't have to have the 0, but it can also be useful to have this. And so the queries, where is it? Queries, you can do prefix sum of 5 minus prefix sum of 2 would be the range of 2 to 5. So 2 to 5 would be prefix sum of 5, which is 14, minus prefix sum of 2, which is 7, which is equal to 7, I think. So something like that. And so you can create a data structure type, or you can just write it within your program, within your main function, just have it like that. And you can find range queries in constant time. So if you know the values ahead of time, then you can pre-compute it in order of n time to create the auxiliary array. And then you can do a range query in constant time. So if you have a lot of queries, if you have multiple range queries, then you might want to use a prefix sum. And one use for this might be things that have to do with contiguous subarrays. So a subarray is one's part of an array, right? And if you need contiguous subarrays, then you're going to have a range of numbers. Maybe you contiguous subarray sum or something, then you might use prefix sums. It's a good idea to think about prefix sums at least. So prefix sum time complexity, it takes order of n. To query a range, it's constant time operation. To update values in the array, it's order of n. So this is important. Let's say you have these values, you set it up once, right? And you need to change the value at 1 or something. You need to change this index value. Then you need to update everything. So worst case time complexity for a point update is going to be order of n. And space complexity is also order of n because you're creating that extra auxiliary array. And you have to recompute the entire prefix sum array after every point or range update. And there are some data structures that kind of let you get around this, but they're kind of complicated and they're at the bottom. Not really going to use those today, but it's good to know about. Additional notes, prefix numbers for if you know you have non-negative numbers, so 0 and above, then the prefix numbers are also going to be in ascending order, right? If you have 0 or greater, then that means that when you have this is always going to be an increasing order. And so you can use binary search on this range. So let's say you have the number 13, you have index 3, and you want to find a subarray containing this index that has a certain sum or something. Then you might try to binary search this range and try to find the difference, something like that. So let's say you want to find a subarray with, I don't know, 6. So you search for the value 13 minus 6. So you search for the value 7, you find 7 here, or maybe you search on the upper end, you search for 13 plus 6, 19. So maybe you look for 19 on the right side. So you can use binary search on this range, but that's given that these are non-negative numbers. Another thing to watch out for is that these numbers increase pretty rapidly. So depending on the numbers within this, so let's say each number is like, I don't know, 10 to the 6 or 10 to the 8 or something. You have really large numbers, right? 10 to the 8, it's really, really quickly gets out of the bounds of a 32-bit number. So if you're using like C++ or Java or something, then probably a good idea to use 64-bit numbers when using prefix sums. So that's just a good rule of thumb. Just check the numbers, and if it's large, then use a prefix, use longs instead of ints or something like that. So you can always do like a sanity check by doing like the maximum number allowed times the maximum array size or something. And then if that's larger than a 32-bit number, then maybe you should use longs. And even if it isn't, maybe it's good to stay on the safer side or something. It's always a point that can break. And you might pass all your sample cases, but you might not pass other cases, the secret cases. And a common mistake is to use 32-bit integers. So you can also do other operations with prefix sums. So it's just pre-calculating in a single direction. You can do like minimum, maximum, you can do XOR. These are all reversible operations. So wait, no, these are not reversible operations. That's something else. But you can do these in a single direction, and you can't update these. But let's say you take, this is a problem from a while back, but it really wasn't accessible at the time. But so what is the minimum height from the left side? Well, this has, or maximum height from the left side, then this height here is 3, the height here is 5. So this is the current maximum up to index 1 or index 2, I guess, mountain 2. And then you don't update the max. So the max at index mountain number 3 is going to be 2 to the left of it or something. You can pre-compute from the right side as well. So 5, and then it's still, max is still 5, max is still 5, max is 7, and then max remains 7. And you can have something like that, and that would work as well. So this is probably easier to do if you know this concept. So I definitely give this a try again, even if it was confusing when we introduced this problem at the start of the year. And let's say you're going to add values across a range and then query last. So another thing you can do is, so let's say customers are arriving at a store. For every customer, you know what time they arrive and what time they leave from arrival to departure. So how many customers are at the store at any given time? So a naive method of doing this might be to have this vector or have an array of time max plus 1. And then from the arrival time to the departure time, increment the time that you're there. And then at every time, you know how many are at that index. And this is worst case n times t. T is the t max and n is the number of cars or something. But another way of doing this is to increment where you arrived, decrement where you left, and then just keep the running sum going for each parked car for each moment in time. So this is a little bit confusing. I think the code could have been written in a different way, but for every moment in time, you can keep a running count. And I should have written out what this looks like, but if you give it a try, I'll do a sample case here. So for this problem, there are 3 cars, A, B, and C. And there are 3 cars, and there's costs associated with parking 1 car, 2 cars, or 3 cars. So there's costs associated with each one, and then you have a start and end time. So you have, like, let's say the first car, it's you stay from 1 to 6. The second car, you stay from 3 to 5 or something, and 2 to 8. So like 2 to 8 or something. You end up with something like this. And then for here, this is 1. Here, this moment in time, it's 2. And here, it's like 3. And this is still 3. And then it becomes 2. And then it becomes 1. Something like that. And so the naive method is to just increment these values. So for every moment in time, from the arrival time to the departure time, you keep on incrementing. So for number 1, you'd increment 1 for every one of these values. And that works, but another way to do it would be, so you have, so 1, 2, 3, 4, 5, 6, 7, 8. And then, so from 1 to 6, so you increment this, so 1, and then you decrement at 6, so minus 1. And then for the second one, you go to 3 to 5, you add 1 here, and then you minus 1 at 5, minus 1. And this is a half open interval. It's also important to note. 2 to 8, 1, and then you're leaving at time 8, so minus 1 or something. Then here, you can keep a running sum. So the current sum is 0, it's 1, it's 2, it's 3, and then 3, and then 1 car leaves, so it's 2, it's 1, and then 0, 0. And if you look back at the previous one, 0 at time 0 maybe, and then 1, 2, 3, 3, and then 3, 2, 1, 0. So 1, 2, 3, 3, 3, 2, 1, 0, 0. You get the same result here. So this is a really useful method to know about. In this problem, the numbers are really loose. So there's only 3 trucks, and the times are between 1 and 100. So you can do brute force. You can use the naive method, but I definitely learn about this. It's very, very useful, and it comes up pretty often. Yeah. So, and then finally, so these are slightly more advanced data structures. The binary index tree, also called Fenwick trees, they have logarithmic time for updates and queries. So you can do a point update range query. That sounds a little complicated. So let's say you go back here. So let's say you try to change the value at index 2. So you want to increase this value, decrease this value, whatever. Then you have to update all the ones to the right of it, which takes order of n algorithmic time. But you can use a binary index tree, and you can do this in logarithmic time complexity. So you can learn about this. So this is super useful, and it takes, I think, n log n to create a tree. So, and it also has a static size, I think. So you can't add later, I think. Yeah, because but there are some like things you need to know about it, but for the most part, it's not too, it's definitely good to know about. Then at segment tree, you can do range minimum queries and range maximum queries. You can set that up. So, and you can update values, I think, for minimum and max queries. So that's more complicated, and I don't know how to use segment trees. I don't think it's necessary for a while. So just good to know that these exist. But yeah. So I think maybe try parking and write it. Yeah, just try parking. It should be pretty simple. And then try this. This shouldn't be too difficult either. So I will pause. So the first two problems are kind of introductory problems with the concept. So I just want to go through one example where this isn't necessarily the most efficient way of solving, but you can actually solve with prefix sums as well. And this is an interesting problem. So so the problem, they're trying to build this altar. It's an interesting prompt as well. They're trying to create an altar to summon someone, and it consists of 3 parts. You have the upper, middle, and lower parts of this altar. And you have n parts for each of the categories. And so you're given basically 3 arrays with different sizes of parts. And to build an altar, the size of the middle part must be strictly greater than the upper part. So you have a small thing, and then you have a larger part and a larger part or something. And how many different altars can you build? And altars are considered different when at least one of the 3 parts used is different. So I definitely give this a try. But a prefix sum. So, but to kind of spoil it a little bit, it's really useful to have these values sorted. The number is 10 to the 5. So you can't do brute force on this and check 1 to n, check 1 to n, check 1 to n. N cubed would be 10 to the 15. That's way too large. You can't use brute force on this. Even if you simplify down by 1 factor, it's not fast enough if you get n squared as a solution. So it has to be faster than that. And so let's say you have just A's and B's. And so I think Sunho. Or if you want to try out, yeah, wait, yeah, there's going to be a recording. So, but this is a kind of, if you've tried prefix sums before, this is not a prefix sum problem. This is a binary search problem to kind of spoil it a little bit, but I use prefix sums to solve it as well. And let's say you have A and B, and if the values are sorted, then for each head part, then you have all your upper part values, and let's say you have your middle values. Then for each value, then you might be able to use all of these values that are larger or something like that. And for something here, maybe you can use parts that are larger. And you can binary search the range where it's strictly larger to have this middle part or something like that. And it must be strictly greater. And so you can use binary search. If this is just A and B, then you can sort both and then do an n log n. So the query for every part, find where you find a strictly greater part in B. So this would be like a lower bound value or something. So if you look at the binary search presentation, like lower bound, the difference between binary search and lower bound to find strictly greater values, it becomes really useful. But you have, but it's not that, right? It's 3 different values, but you can actually pre-compute for every value in B. So, and then think of C as doing it over B, and then add the values for each B. That's probably confusing, but so for B, you can rewrite this as for each B, how many head values work? And then, so you get the number of combinations per piece in B. And then you can do C, you can do binary search on the sizes of B and add up the range values for B. So if you find, so you have your parts for C and you have your larger parts or something, you have your larger parts. I don't know if C is larger or smaller, but okay, lower is C, okay. So you have a larger part C. So for something here, then maybe you can only use these values, which are strictly smaller. And then for here, maybe you can only use one value or something. Or something here, maybe you can use all of these. And then for here, for each value, you have maybe you can select up to like 5 or something. Maybe you can have 4 A parts that you can choose. Maybe you have 3, 2, 1 or something. And then you can do a range sum to and you can pre-compute how many values, how many A parts there are, and then create a prefix sum and binary search on this range and add up values. That's a convoluted way of doing it. So you can do this with prefix sums. And then just the binary search solution would be to, you have the B values, you have the A values, you have the C values, and then you can start with the B values and find all parts that are strictly less and find parts that are strictly larger. So this is the simplest solution, which is definitely better, but and a lot easier as well, but you can use something like binary search and prefix sums to solve this as well if you want to turn it into a question of like simplifying it into from A, B, and C down to like B and C. How do you simplify it into that? If you do it in that process, you can use prefix sums to kind of do that. And yeah, that's another approach for it. But I definitely try this problem out. It's pretty interesting. And it's part of the Division 2 practice problems. Definitely check these out. And restaurant customers, this is another similar problem to parking, except it has larger constraints. So definitely check this. And this is a good way to test this range update query last. So this is literally the question I'm writing here. Customers are arriving somewhere and they depart sometime. How many are at any given time? And you're giving arrival and leaving times of n customers. What's the maximum number of customers at the restaurant at any time? So this is the exact same problem, except you take the maximum of the range of the prefix sums. Kind of like a prefix sum, but similar concept. And there are some like more difficult problems as well. So you can actually do prefix sums on 2D ranges. This one only requires n squared solution. I think you can do it with one prefix sum from what I saw, but you can actually do 2D ranges of prefix sums. So that's also something to learn about. We talked about Bungee Builder and taking maximum and minimum from a certain direction. So from 1 all the way up, from the n all the way down, you can take maximum or minimum. You can find the maximum from the right side, maximum from the left side or something. So that's something you can do. What else can you do? And this might be somewhat similar to the problem where you have the parking and the customers and stuff. This kind of updated value, this is maybe more of like a map or something, a set or something, but we'll have these questions up. And this is kind of difficult. But find the number of non-empty contiguous subsequences of A whose sums are 0. So you have this range and then count the number of ways that the sums become 0. Now this is, yeah, this is, you do prefix sums and then it requires another step. So it's kind of hard, but really interesting as well. But basically, if you come up with a question about contiguous arrays and contiguous substrings and things like that, then prefix sums are probably something you should consider. Counting something across a range or anything that requires a lot of queries, it's something to consider. And if you have to update in between, then maybe you have to use a more advanced data structure. So yeah, but the original concept isn't too difficult. You just have this auxiliary array that adds up the values, and then you subtract the range. And this is also another, it's also another really useful tool for when you come up with more math problems where like, uh, like count the number of ways for a sequence or something, and then between values of like A to B or something. And then a lot of the times you can do, or I don't know, you have this A to B range, and a lot of the times you can calculate the value for 0 to B, you can calculate the value for 0 to A, and then like range B minus range A will be equal to A to B. So if you have some kind of consistent sequence of numbers and you need to calculate values between A and B, so it might be like primes, it might be some kind of thing, then a lot of the times you have to do RB minus RA, like 0 to B minus 0 to A. So it's kind of similar to the prefix sum concept as well. So it's really, really useful and very versatile in a lot of different uses. Yeah, but I think that's about it for prefix sum related stuff. The only thing is like there's a lot of variations and it just gets way harder. Just you can do a lot with this, but it's kind of, yeah, and it gets way complicated. But the underlying concepts are based on the same principles. And I guess we'll talk about binary index trees a little bit. So you have this array, right? You have an array. Then if you want to take the array, symmetry is based on prefix sum. Yeah, yeah. Which, yeah, it's kind of, yeah. Segment tree. So let's say you have array values, right? You can consider these nodes, you can have it in. So a binary index tree just has stores the sum of two individual things or something. And you have these pairs. And I should do a power of 2, to be honest. Okay, and then here, so basically you have, when you do a range, you can do a point update in logarithmic time because let's say you want to update this, right? You only have to update here, you update here, and you update here. And so you do maybe like, let's say you +1 on the value, then you add 1 here, you add 1 here, and you add 1 here, right? And you can do this, and this, the height of the tree is log n. So this is a logarithmic update. And then let's say you want a range query, then you just find some place and then like this range or something of numbers, and you can subtract away one thing or subtract away this thing or something. You can find a range query in logarithmic time as well because you're kind of traversing down a tree, and it's based on the prefix something. And this is a binary index tree. And the so this is the principle behind binary index tree. Then segment tree, I don't know. I don't know. I don't know enough to explain, but you can do min and max. But the problem with min and max is that let's say the current maximum is this value and you decrease this value, right? And so maybe you can update this and it'll be accurate. You can update here and, well, it's the maximum between here and here or something. It's not necessarily reversible. So it can be, if you're only increasing values, it works. But let's say you're decreasing a value, then this becomes larger and then you have to compare with the previous one or something. There's just moments where it doesn't work. That wasn't a good explanation, but minimum and maximum range queries are kind of difficult. And so it's a problem called like RMQ, like range minimum query, maximum query or something. Yeah, I definitely don't know enough to explain, but you can do range, and you can also do range update range query. Binary index tree can also be modified to do range update range query, but you can learn about here. But segment trees, lazy propagation segment trees can do range update range query as well. And if you scroll down here, you can find you can have two binary index trees, and I don't know, I don't understand it, but it supposedly you can do range update range query with binary index trees, but I haven't really looked into it. It's good to know that these things exist, and this is the power that the tree structure, right? Why do a lot of algorithms rely on some kind of tree structure? It's because it makes it easier to speed up things. And you only have to update for this one root or something, and that's only logarithmic. So that's why tree structures are really common for advanced data structures. Yeah. I think that's about it for prefix sums. Yeah, so I think I'll pause.